Okay, so as I mentioned in the last video, we're going to talk about a method of finding derivatives known as logarithmic differentiation. Now, as I've written here, sometimes finding a derivative with the rules that we've developed so far is very complicated or impossible. For some of these where it's complicated to use any of the rules, we're going to use a technique it's known as logarithmic differentiation, which makes use of the properties of logarithms to basically simplify the product or the function before differentiating. Simplify the function and then implicitly differentiate. So first of all, I want you to recall the properties of the natural logarithm. I'm going to use the natural logarithm when I do logarithmic differentiation. You could use log base something other than e, but if you remember, the derivative of the natural log function that we learned in the last video is nice. It's just 1 over x, and so that's what we're going to use in this process. So if you remember these three properties for logarithms, the log of a product is the sum of the logs. Of course, that comes from, if you remember, logarithms are what? Exponents. And when I'm multiplying two bases, right, what do I do with their logarithms? Their exponents when I multiply the bases. I add them, right? I add their exponents, right? So that's why the natural log base e of uv is equal to natural log of u plus natural log of v. Natural log of u divided by v, the log of a quotient, is the difference of the logs, and that's because, again, if I'm dividing like bases to different powers, we subtract the powers. We subtract the logarithms. Again, logarithms are those powers or exponents on the base. And then here, the natural log of u to the n is n times natural log of u. So in other words, what are we saying here? If I raise a exponential expression to another exponent, what do we do with the exponents? We multiply, right? So I'm raising u to the n, so I'm going to do n times the exponent on u, which is the natural log of u. N times natural log of u. The way we remember this rule is kind of like this n comes down in front. It brings it down. Okay, so these are the properties you should remember from pre-calculus. And we're going to use this method then to find the derivative. Now, in each of these cases, the first one here, the derivative of this function can be done without logarithmic differentiation. Okay, it can be done without logarithmic differentiation. But what rules would I have to use to find the derivative of this function if I tried to do it straight up? So I hope that your first statement may be, I don't know, quotient rule, because I've got a quotient. And then what do I have up top here? X to the fourth times the square root of 3x plus 2. That's a product. Put a product in there. And then I also have chain rules, right? X squared minus 1 to the fifth power, right? That's a composition there. Square root of 3x plus 2, there's a chain rule in there. So you just got a lot of stuff going on, so it can be done, but the derivative process is quite involved. Okay, so what we're going to do is we're going to use the properties of logarithms to get to an expression that's to make the differentiation process easier. Okay, now we've got a little bit of algebraic work to do here using these properties. So what I'm going to do is I'm going to take the natural log of y, which would be then the natural log of all this stuff, and I'm going to write the 3x plus 2 square root, change it to the 1/2 power, and then we have x squared minus 1 to the fifth power down here, right? So when I take the natural log of all this expression, right, since both these things are equal, their logarithms are the same, so that's where we're at. But this expression that I can simplify, first of all, I'm going to use property number 2 up above, because the log of a quotient is the difference of log. It's the log of the top expression minus the log of the bottom expression. So I've got the log of the top expression minus the log of the bottom expression. Okay. And then when I look at this thing, well, that's a log of a product, right? X to the fourth times 3x plus 2 to the 1/2. So the log of a product is the sum of the logs. So again, I'm going to expand. It's really simplifying though in a way. Because I'm breaking up, so the log of a product is the sum of the logs of the individual expressions in here. Right? So I'm simplifying in the sense that basically I've broken up product, got rid of the quotient. I don't have a quotient anymore, so I'm not going to have to use quotient rule. I broke up the product. I'm not going to have to use product rule anymore. Okay? So I'm trying to alleviate things. Now I'm going to make use of the last rule here. Right, natural log of u to some power, the power comes down as a multiple of the logarithm. So finally I get natural log of y. This 4 comes down as 4 times the natural log of x. This 1/2 comes down. And this 5 comes down in front as multiple of the logarithm. Okay. So I'm basically, if you remember from pre-calculus, expanding logarithmic expressions as much as possible. That's what we've done. That's what we've done here. We've expanded this as much as possible. And now, we are now ready to take the derivative. So at this point, I say, let me take the derivative with respect to x of both sides. What am I doing? Implicit differentiation. So over here, notice I've got a natural log of y, and I'm taking the derivative with respect to x. Derivative with respect to x. This is a chain rule, because y is a function of x. Inner function y, outer function natural log of y. So the derivative of the outer function natural log of y, remember, is 1 over y, times what? The derivative of the inner function, which is just what? dy dx, or y prime. Now, over here, all I have is x, right? Stuff involving x, no y. So we're just straight up take the derivative. Now, what do I have? I don't have any quotient rule. I don't have any product rule. I do have some little chain rules. Okay, and we'll see that. First of all, what's the derivative of 4 times natural log of x? So we've got just sum and difference rule to start off with. Well, 4 is a constant multiple times what? The derivative of natural log of x is 1 over x. So it's the derivative 4 divided by x is the derivative of 4 times natural log of x. Plus what? What's the derivative here? 1/2 is a constant multiple pulled out. And then this is a little chain rule, right? Log of u. At the end of the last video, I talked about the fact that log of u is going to be what? 1 over u times u prime. So 1 over u is 3x plus 2, times u prime. What's the derivative of 3x plus 2? Just 3. So the derivative of this log of u is 1 over u times u prime. 5 is a constant multiple. Same thing here. What's the derivative of natural log of u by chain rule? 1 over u. 1 over u is x squared minus 1, times the derivative of the inner function u. What's the derivative of x squared minus 1? 2x. Okay, so I'm going to do two things. First of all, to solve for dy dx, what do I need to do? I need to get rid of this by multiplying both sides by y. So I've got dy dx is y times what? Well, let's clean this up. 4 times 1 over x is 4 over x. 1/2 times 3 over that, I just have 3 over 2 times 3x plus 2, minus 5 times 2, 10x. Right? Okay. So I've simplified all that. So I did have a lot of work to do to simplify it, but then when I took the derivative, not that hard. Derivative, not that hard. Okay? So that was the whole point of this problem, was to make taking the derivative easier. Now, one last thing, dy dx, as we do with implicit differentiation, we get an answer in terms of not only x's, but y. If I can express this in terms of x only, I should. And I can very easily, because remember, y was what? That was our original function. Y was all this stuff. Right? So our actual answer is dy dx is what? Y, the original function, which was x to the 4th square root of 3x plus 2 over x squared minus 1 to the 5th times all this stuff. And I'll just rewrite this stuff. So that's a lot of work, you might think. Oops, sorry. That's a lot of work there, right? So again, y, the original function, x to the 4th square root of 3x plus 2 divided by x squared minus 1 to the 5th. I just rewrote that for y, and then times all this stuff, rewrote that. So you say, wow, that's a lot of stuff. Yeah, it is. Now, I don't have to use logarithmic differentiation, but if you go back to the original expression, you might want to try this. Try and use quotient rule, product rule, and chain rule, all that going on. It's pretty messy, and to try and simplify it down to something like this, probably not going to happen. Okay. Now you can simplify this further algebraically if you want to. Now I would not want you to do that in this case. But here's an example of using this process on a problem that is very difficult to find the derivative directly by our rules. Okay. But the next two I'm going to show you, it's actually impossible to use the rules that we've developed, and so logarithmic differentiation has to be done. These two examples actually look a little bit simpler. And let's take a look at the first one. Let's get our properties up there again so we can refresh our memory about those as we proceed. All right, x to the x. Okay, what's the derivative of x to the x? Well, it's not power rule. I can't just bring the x down and subtract 1 because the base is variable. It's not the exponential rule. Remember the a to the x, which was natural log of a times a to the x was the derivative? That doesn't work because now the base is not a constant, right? So if the exponent's a constant, we can use power rule. If the base is a constant, we can use the general exponential function rule. But neither is the case here. Okay? So we have to do logarithmic differentiation. So remember how that works. I take the natural log of both sides of this. Okay? And then I simplify this expression using the properties of logarithms. And I use property 3 here, right? Natural log of u to the n is n times natural log of u. So natural log of x to the x, exponent comes down. I get x times the natural log of x. So real important, this is now a product. And now I can find the derivative implicitly, right? Using the product rule over here on the right. So now I use the implicit differentiation process. What do I get here? Well, we saw this one in the last problem. I get chain rule, right? Derivative of the outer function, natural log of y is 1 over y, times the derivative of the inner function, dy over dx. Over here, right, I've got product rule, right? This right here is going to be product rule. So I've got the derivative of x times natural log of x plus x times the derivative of natural log of x. Derivative of x is 1. Derivative of natural log of x is 1 over x. Okay. So let's clean this out. Again, I'm going to solve for dy dx. I'm going to multiply by y. So dy dx is y times what? Put all this in parentheses. 1 times natural log of x plus x times 1 over x. X times 1 over x is just 1. Okay, there's my dy dx. Notice it's in terms of x and y, but I can make it in terms of x only because y is just x to the x. So if I write y as x to the x, there's my derivative. So quite a little interesting function, x to the x power, and we are able to find its derivative. We'll do one more like this again. What about the natural log of x raised to the natural log of x power? Well, we're going to proceed the same way. Take the natural log of y, and that's the natural log of x raised to the natural log of x power. Now there's lots of natural logs over here. Understand this is the natural log of all this stuff, right? And this stuff is natural log of x raised to natural log of x. But the rule we're going to make use of again is number 3, right? I've got a power on my natural log of x, right? And it is, natural log of u to the natural log of x. So there's our u and there's our n. This n comes down. This exponent comes down. So it's going to be natural log of x times the natural log of the natural log of x. Be careful. This is not multiplication here. It's multiplication here. I'm emphasizing that with the dot. This is the natural log of. This is composition here. Natural log of x times the natural log of the natural log of x. Okay, so again, making use of that third property, right, to bring the power down, where in this case the power is the natural log of x. Okay, so now I can actually use implicit differentiation. I take the derivative with respect to x of both sides. Right. This again becomes 1 over y times dy dx. That's the chain rule. Right, so again by the chain rule. I've seen that several times. And then over here I've got product rule, right? So I've got the derivative of natural log of x times the natural log of the natural log of x plus natural log of x times the derivative of that thing. Right? And so this is all going to be, this is product rule again for this part. Okay, so what's the derivative of the natural log of x? So we know that one is 1 over x. What's the derivative of the natural log of the natural log of x? Well, that's chain rule, right? Chain rule here. Another chain rule. Natural log of u, right? Outer function is natural log. Inner function u is natural log. So both the inner and outer function are the same. So the derivative of the outer function is 1 over u, which is natural log of x, times the derivative with respect to x of the natural log of x, the inner function, which is 1 over x. So this becomes 1 over natural log of x times 1 over x. But now when I multiply by natural log of x, what happens? The 1 over natural log of x become, this product becomes 1. So this whole thing over here after the plus sign is just 1 over x. Solving for dy dx. Multiply both sides by y. And I have basically what? Natural log of the natural log of x all over x, right? 1 over x times that. Plus, and what do we say here? Natural log of x times this is 1. Just 1 over x. And then I can write this finally in terms of x only. Remember the original function y was what? The natural log of x raised to the natural log of x power. So that was the original function y up here. I just replaced y with its original expression in terms of x. And then over here I'm just very tempted, since I have a common denominator, to go ahead and just add these fractions together so that I can write it a little more compactly, right, all over the common denominator of x. So there is my derivative. Okay. So logarithmic differentiation will require some practice. There are some examples in our textbook, and there's a couple of ways of kind of approaching the logarithmic differentiation. The book, I think, presents 2 methods. They're essentially the same. So I'm doing one of the methods. You can look there and see how they do the other way. But for these last 2, there would be no way to find these derivatives with the rules that we have until we, unless we use the logarithmic differentiation, we're not going to get anywhere. So a very helpful thing to find derivatives of expressions, functions who are exponential expressions where both the base and the exponent are variable. Okay. So this basically really finishes up our whole discussion on derivatives, and the rest of the course from this point forward is really going to look then at applying derivatives. But in order to apply the derivatives, in order to use them to do stuff, you've got to know how to find these derivatives using all the rules we've developed. And so that's going to be an essential skill for you as we move forward. Okay.